I was right now. All right. Hello, everyone. Thank you for coming. Welcome to our last workshop of the week. Today we have a great speaker. Her name is Lucy Zhao. She is the former co-lead for Freetal and a really awesome person studying natural language processing. So without further ado, I will let Lucy take it away.
Thank you, Anj. Yeah, so for the scope of this talk, I'm going to be focusing on methods that you can get spun up like very quickly and giving you a broad overview of methods in natural language processing. And of course, like if you do want like further background knowledge, there's a huge variety of good lectures from like different universities out there. And even here at UT, there's a professor, Greg Durrett, who teaches a really good undergrad NLP course. So if you want like more theory, that's where you would look. For this talk, I'm going to focus on general concepts, general tools that people have built to do NLP. So when we talk about NLP, it's natural language processing means that we're trying to solve problems that require understanding text in some way. And so the very high profile, really fancy problems that you could solve have to do with maybe like search and question answering. So if you input what is retail hackers into Google, you actually get what's called a knowledge card or like a snippet that picks out this passage answering your question. So it says retail hackers is a student organization at the University of Texas at Austin, yada, yada, yada. And obviously you could think about the complexity of this. First has to like identify what kind of question or what kind of answer the user is expecting. Then it has to go and parse the trillions upon however many documents Google indexes to actually find a candidate document with the potential answer and then parse out the passage that contains the specific phrase that you're looking for. So another high profile application of this it has to do with dialogue systems, or maybe you've seen like the tweet bot that Microsoft also comes out with. So this is Microsoft Zhao. And this is an interesting example because here we have dialogue that's like very colloquial, right? So waves, and then this person's like, I hear you're a big Jonas Brothers fan. And Zoe will respond with like emojis and like, you know, shortened versions of words like the letter U or like TBH and et cetera, et cetera. So this is all very cool. What's actually happening behind these systems? So when we're talking about NLP systems, what they seem like to us are like usually black boxes if you haven't really studied in depth, if you haven't studied very in depth on a topic. But in practice, what you have are usually what's seen on the left. So these are very like fine-grained components that I link together into pipelines. So what you'll do if you're trying to create a search system or a dialogue system is that you'll take the text input, you'll have all these steps like clean the text, maybe filter out like inappropriate content that you don't want, and then like convert it to templates, and then finally you'll have like some complex system to interpret it. So this could include like hooking it up to a knowledge base or pulling in like outside information that you'll do before you finally generate the output. So most of these like high profile cases will tend to have these like engineering layers built off of it to achieve like some sort of production quality, right? So some advantages of this are that like it's easier to debug and potentially de-bias, because if you think about like all the cases that like make headlines where machine learning like learns like racial bias or gender bias based on its training data, that obviously generates like negative PR, and that's very hard to diagnose. So in practice, you'll usually go with like a fine-grained like pipeline system. And then for these systems, each piece can be implemented individually to your needs, or you can use some out-of-the-box system to do each of these processing steps. And I'll show some examples of NLP libraries and what they can do. And to sort of hook together a pipeline like this. And finally, if you're running Google search or if you're running like a chatbot, you don't want any delays. So you really want some systems that are low resource in terms of compute. And often if you're working on a new project, you may be working in a data scarce setting where this sort of approach will come in as well. Okay, so that's that. And on the other end, you have these sort of like black box systems that are like very impressive. These are the ones that you read about on like maybe Tourist Data Science has like a new article on the state of the art, like the machine learning method. And all you do is you feed in like an input image or an input passage and like it spits out something amazing. So these can be less engineering focused. They're much harder to debug. Obviously, very high resource if you think about it. And then you have this problem of extensibility. So yeah, and then once you have some sense of the most recent tools on both sides of this equation, because you can like string together your own pipeline for an NLP project, or you can try to like train or fine tune a network from scratch if you have enough data and if you have enough resources. But once you have knowledge of both these approaches, you might be able to determine how to actually build a system for your specific project. Cool. For conceptually, when we're thinking about natural language processing, we want to be thinking about representations. And this is especially important if you come from a general machine learning or a general like computer vision background, because vision is very nice because images are naturally represented as vectors, and they have like absolute values, absolute pixel values, right? For natural language processing, the task of representing words as vectors is a bit more ambiguous. First of all, like, how do you do that in a reasonable way? And second of all, how do you deal with the ambiguity of language? For example, like different words can have vastly different meanings depending on their context. And each passage of text is subject to like different interpretations between people. So that's why NLP is hard. And that's why improving NLP usually comes down to better representation. So how can we extract better features through syntactic parsing? That could be part of speech tagging, dependency parsing, some sort of like co-reference resolution, so you could tag which entities are referring to the same thing. And then once you have some sort of sensible annotation or embedding, then it becomes much easier to pass it through like a system that can interpret and generate output, because you've taken this amorphous thing and you've given it structure by converting it to vectors or just tagging it with things that like you would expect to see and that you can build a rule-based system off of. Okay, so as I said, this talk is going to be a toolbox to approach natural language problems. There's not going to be too much theory about like how these tools are implemented. I will give a lot of like resources at the end that like if you want to figure out how they're implemented, and I encourage you to do so, because then you could weigh like the different implementations for a specific tool that you're trying to use. And so I'd be sort of trying to give you an idea of the concepts required to do NLP, because it does rely on some sense of understanding of just like language and grammar, as well as most recently how those fit in when you interact with like neural networks that you can train. So I'm going to be doing this by doing this elaborate thought exercise where we're going to try to build a search and question answering system together. Yay! Okay. So how would we go about building a basic search and QA system? So think like Google. we're going to assume that you have the web crawling part down because there's not too much NLP there. So you have like a bunch of documents and you want a way to like query and search and answer questions from these. So in this first phase, we're going to focus on using out-of-the-box tools to process the text. And for step one, we would want to index these documents for faster searching. And this is something that most sensible QA systems do. So you're not doing this like crazy thing where you're like searching through all of your each document to like phrase match at like every search query. So this might look like just like indexing by named entities or common phrases. So you would match like the phrase retail hackers in all of these documents, or match Abraham Lincoln in all of these documents, and etc. Obviously, it can get a little bit more complicated. So for example, if you go to any popular search engine and you search for 3D printing, it's going to match on terms that don't always have the same stem. So it'll match on 3D printers or 3D printed, or different variants of that. And so this introduces an important step when we're doing an initial text processing, and that's sort of this cleaning and stemming and lemmatizing step. So what this does is it'll sort of like clean your text in a way and get to the root form of words so that like it can be easily standardized across all of these like text documents that you're processing. Okay, so once we have all of these documents indexed, now we can go on to this idea of handling basic questions, because if we have an index, we can sort of just search for key phrases. We know how to do that. We can stem, we can get the lemma, and then we could just like pattern match, right? What if we want to handle basic questions where we're looking for information, specific information about an entity? If you're first coming to this, like it's very straightforward that you can like match a template. So you can look for questions in the form of who or what is X, and then you search for X is, was, are, the answer, and you might get a document retrieval that looks like this. So that's fine. But not all of your documents will be so pretty and it will always match your template, right? So what if you have a document that has maybe an appositive phrase or an extra clause that to us like seems very extraneous and doesn't really change the relation between Freetal hackers and the phrase "is a student organization." So for a lot of NLP tasks that you're going to try to do, it's really important to understand this idea or have some sense of syntactic parsing. So we're thinking about syntax, we're thinking about grammar, and one of the most useful ways, one of the most useful forms of this is creating dependency parses. So that'll look like the output of that will look like some sort of dependency tree where we will identify sort of the root of the sentence, which is usually the main verb, and this sort of tree structure of modifiers, right? So we can see here that the main verb here is the word is, and that connects retail hackers and a student organization, these two phrases. And furthermore, we can see that like all these other phrases will, such as the phrase pictured above, modify retail hackers directly. And also we can get part speech tags for all of this. And so if you're doing something that looks for that like is contingent on like matching specific like maybe triples or like subtrees of specific like part speech tags, maybe you're trying to try parse relations, so you're looking for specific verbs that connect different entities. This is a great way to start, is looking at some sort of syntax tree, some sort of syntax parse, and then trying to mine that for information identifying patterns that will that will help you with your task. Okay. Another big tool that is commonly used is co-reference resolution. So obviously, we like for human beings, it's like very natural to interpret these to interpret co-references, which is when like different words or phrases in a passage refer to the same entity, right? So here is an expanded document that talks about Freetal hackers in the first sentence, and in the second sentence, it talks about how it's made up of students from many different backgrounds, and they host hackathons where students can learn regardless of skill level. To you and me, it's very obvious. Okay, they means Freetal hackers. But if you have a lot of these co-references if you have a lot of like different pronouns and different entities that they could be referring to within the same passage, it gets a little bit difficult. So luckily we have tools for co-reference resolution, which will annotate these clusters of phrases that refer to the same entity. So here it will tag both Freetal hackers and the pronoun they with the same entity. And you can look up Allen NLP co-reference resolution to see a really good demo of this. And I really recommend Allen NLP's demos because they are very pretty, and they also give you the direct code of how to run these parsers yourselves. So that's also an important tool. So that's just that of course is a small subset. I encourage you to look more into the types of parsers that are available out there. But when you're building a NLP pipeline for a basic task, it'll come down to these steps of cleaning, and then you'll annotate it with some like syntactic information, or maybe like learning information if you have specific like sentiment tags or other classifications that you want to do, and then you'll put it through a different system to actually like take actions upon that text and those annotations. So if your NLP project looks, if you can like in a defined way break down your NLP task into a pipeline of different steps, like I've shown you in the past few slides, and then pass that through maybe a rule-based system, then I would recommend that you look at like these following tools in order to help you do that. So NLTK stands for Natural Language Toolkit. It's pretty good for stemming and lemmatizing and data cleaning in general. Allen NLP is going to implement state-of-the-art like neural parsers, so that you can get like prior speech tags, dependency parses, constituency parses, and etc. So Spacey and Stanford Core NLP I don't use as much, but they also implement a lot of the same like parse structures and functions. Okay, so now that we've gone through this like whole thought exercise of how we might approach building a QA system, now we're going to look at like what state-of-the-art like fine-tuned language models can actually accomplish. So this is a demo of a model called Transformer QA from the Allen NLP website. You can go here if you wish. And basically what this model does is it takes this passage in the question as input, and it does some basic like processing before it feeds into the model. So it'll split it up into like word tokens, and then it'll convert it to vectors, and then it'll pass it through the model. And what you get as output is the span within the passage that contains your answer. So this model predicts a start span and the end span of where it thinks the answer is contained within your passage. So this is a very simple example. You can explore other examples on this demo website. So this is talking about the Kerbal Space Program. And the question is, what does the physics engine allow for? And the answer that is predicted is various real-life orbital maneuvers. So this is all very impressive, right? So instead of us having to really like hyper engineer every step of determining a reasonable like question input representation and then figuring out how to like parse the passage and then look for the type of answer that we're expecting, it's very nice to just have a model where you can just like plug and play. Obviously, this sort of thing is not feasible for, I guess, all of the natural language projects that you're going to have to use, because we only have like high quality data sets for a specific set of tasks. So another place to start, if you want to integrate natural language processing into a project, would be looking at tasks in which like researchers out there have already figured out how to do pretty well, and then using that to enhance the system, right? So maybe you want to do some sort of sentiment analysis on a comment section, or to maybe like rank or filter out different comments to, to figure out like which ones to flag or which ones to make visible. Maybe you want to summarize a bunch of documents or a document to present like a little abstract for someone to read before they click through to a full page. Of course, like maybe you want to improve internationalization of like a website or a project that you're working on, and then you'll look at machine translation tools. So the list of tasks that people have studied like in depth is pretty expansive, and it ranges from like very coarse grained, so summarization, machine translation, search, and question answering, to very fine grained. And if you want just a topic list, you can go to this website that I recommend. It's called nlpprogress.com, and it'll basically list this huge variety of natural language tasks that researchers have worked on, as well as state-of-the-art data sets and performances for those. So if you're more literate in maybe neural networks, this might be a good place for you to start pouring through some data sets or looking at what kind of architectures are being used right now to solve certain problems. Finally, I think the takeaway from this comparison of the pipeline approach versus the black box approach is that whenever you're approaching a natural language problem, you should be asking if your problem can be solved by using a few natural language analysis tools. And this includes the ones I showed above, as well as like the other tools that you could find in Allen, NLP, and Spacey, and etc. And if so, it might be easiest to go that route if you don't need anything like too sophisticated that requires like linking together several different representations. Secondly, you might want to ask, can you use an existing system or adapt it and take advantage of what researchers have already learned to do well? And these systems can be both neural networks, black boxes just trained for specific tasks, such as like question answering or sentiment classification, or they can be more pipeline systems. So there are tools out there that can generate knowledge graphs from, or extract triples from documents. And that saves you the trouble of having to like build a system yourself to extract information. So if you're answering no to both of the above questions, or if you want a fun learning exercise, I guess, then you might want to train your own natural language model. I'm going to caveat this with the fact that like, well, this is very fun. And today it's pretty simple. It's not always good if you're trying to come up with an like shippable product. But we'll get into it anyway because it's very cool. And that's like mainly the realm where I work in instead of the application side. So this final section is going to be on training neural networks for natural language processing. And for this, I'm going to assume that you guys have some sort of background on training neural networks, just so we can get to the natural language specific parts here. Okay, so when we're thinking about training a model for natural language, it probably looks something like this in your mind. You take some text that you care about, you put it through a neural network, and then boom, you get the answer. And in this neural network, you'll do all that fancy stuff like, oh, you'll figure out like what architecture you want to use, and you'll figure out the input and output, mainly the output representations that you want to use, and et cetera, et cetera. So, but that's fine. Yeah, you can copy like architectures that you find online or take inspiration from them or whatever. What I'm going to go into here is this idea of like word embeddings, right? So when people come from a general ML background, they usually have more experience with vision, and it takes some knowledge of how to integrate your like natural language intuition and knowledge into models to be able to train like a sensible model for natural language. So I'm going to go into word embeddings. So how do we turn these words into vectors that we can then operate on? And then finally, I'm going to go into what most people use today to get like what most researchers use today to get like really good results on benchmarks, which is this idea of like pre-trained models. So let's get into word embeddings. Fundamentally, we need to take text and we need to represent it as vectors. At minimum, each unique word should have a unique vector representation. This seems pretty straightforward, right? Because each unique word is probably going to have a different meaning. But aside from that, we've learned how to do this in a very, say, like useful way. So in practice, what you would want to do when you're building a natural language model is that you're going to download from the internet a set of pre-trained word embeddings. So someone else has created this this mapping from words, from common words to vectors that captures some like semantic meaning, right? So two of the most popular pre-trained word embeddings out there and methods of training them are GloVe and Word2Vec. These terms refer to both the method used to train these word embeddings as well as the word embeddings themselves. In practice, you're just going to download the mapping from words to vectors that they've already produced. And so what you're doing with word embeddings is that you're taking a word and you're projecting it into this like high dimensional space. And these word embeddings end up having special properties, right? So if you go to projector.tensorflow.org, you can see a very good visualization of Word2Vec specifically. So here I've searched for the embedding vector that represents car. And out of, I think this is like tens of thousands of vectors in Word2Vec, it's found the like top 100 or so other words in the Word2Vec that have like the highest cosine similarity. So these are like the closest vector representations in Word2Vec. And you'll see that these happen to be other words that are somewhat related to car, right? So you have over here, you have driver, you have cars, you have automobile, race, etc., etc. So this is very nice. This is much nicer than if you tried to just like come up with like a random mapping from words to vectors, right? And we can look at this like even more fine grained. So over here is a visualization where they've done like PCA on these like nearest neighbors, and then they projected them across the most meaningful components. And even within this small subset, we can see that all these words that have to deal with like airplanes, such as plane, aircraft, helicopter, just happen to be at like this one area of this visualization. And then we can also pick out like, oh, there's this one like hotspot where we can identify all these words that have to deal with like railways and rails and trains and locomotives. So this is very cool. And furthermore, in addition to just putting different, giving similar words, similar embeddings, you can also pick out these analogy relationships with word vectors. So this means that similar vector difference will exist between corresponding word pairs, right? So if you take the vector representing king, you subtract the vector representing man, and then you add the vector representing woman, that will give you some vector representation that will be that will have as its closest neighbor the vector for queen. And then there's a bunch of examples for this if you just want to search online. It's like very cool to observe. But all of this serves as intuition as to why you should use pre-trained word embeddings when you are training your own natural language model. So in practice, what you would do is you would take the text that you care about, you would map it to these pre-trained word embeddings that you've downloaded from the internet, and then you can pass these through a simpler neural network than you would have used before that will transform your input to your output dimensions and will give you some sort of sensible answer. And then for a lot of applications, this might work pretty well if you're just trying to build a simple classifier and you're trying to explore, maybe do some exploration of neural network architectures. This could be all you need. This is a good place to start. There's a widely held belief, I can neither confirm nor deny, that when you're training natural language models, your neural network structure should sort of mirror the structure of the text features that you're inputting. So there could be some experimentation there based on what you want to do. So, however, when we're talking about the most impressive results that we can get today, we have to talk about pre-trained language models. So instead of just using this like static mapping of words to vectors, we're going to take the text that we're using as our input, and we're going to be putting it through a pre-trained language model. And on top of that, we're going to attach maybe a small classifier or maybe a couple like linear layers that will transform the output of the pre-trained language model to our correct, to our desired output for this task. And we'll train both of these in unison, right? We will backprop through both this like top layer, and we'll backprop through this giant pre-trained model that we've now plugged in. So the idea behind pre-trained models is that these are large models usually trained on like huge amounts of data. So the most notable one for NLP is BERT, although it's not the state of the art anymore. But when BERT first came out, it took something like days to train, and it was released, of course, by Google, which is usually known for having infinite resources and infinite compute. So you could just imagine like how many GPUs or TPUs they threw at this thing. So when people train these like pre-trained language models, they release both the model architecture and the weights, so that you can load this model that already has some sensible information about semantics and about language already learned. And the idea here is that the general aspects of natural language, of how to interpret grammars, how to disambiguate between different words based on their context, the general idea is that this can be applied to like any downstream natural language task that you might care about. And in practice, this works really well. Before like BERT came out, the leaderboards for the benchmarks that we use to measure like how much progress we've made on natural language looked very different. but now if you go to the question answering leaderboards or the sentiment classification leaderboards, it's all been taken over by some sort of pre-trained model, and typically a transformer-based model. So without having to read like the 8-page paper that talks about BERT or any of its like derivative architectures, you can still use these language models. You can basically treat this as a black box when you're fine-tuning to a specific task. And there's a couple of blog posts that link to how to do this, and in particular there's a bunch of collaboratory notebooks that show you how you can load the pre-trained model, modify the model architecture by usually adding just a couple layers on top, and it'll show you how using existing data sets you can just fine-tune for a few epochs and achieve like amazing results on a downstream task. Obviously, this requires that you have the resources to actually like train these models. So even though you're only training for a few epochs, the size of these models means that it takes forever. But if you do have the resources, if you can like use the Google Colab GPUs, or if you have even a GPU on like your own laptop or a machine, it might be feasible to do this. Of course, you'll probably need some amount of data for your specific task, usually around like on the order of like a couple thousand to like maybe 10,000 examples. But I encourage you to give this a try because it's very cool. So finally, I'll wrap this up so that we can like take questions. Here's some more resources on what I've just talked about. In particular, if there's one thing that I want you to take away from this, it's this guy named Alammar's blog. This was instrumental for my understanding when I first started doing NLP. And he has like these like beautiful explanations of a lot of like important NLP concepts. Here's some, if you're for like practically like training your own models, you can find the sources for GloVe and where to back and where to download those here. Of course, plug to NLP Progress. And if you're going to be fine-tuning a state-of-the-art transformer model, I highly recommend looking into the Hugging Face Transformers library, and because that like provides such an easy, like straightforward interface for you to load these models, switch them out, and then also add on top of them. So are there any questions?
There was one question in the chat that I actually missed from a while ago. But back in part one, when you were talking about the search engine stuff and you were talking about searching for something like a query like what is Freetal hackers, right? The question from one of our attendees is, how does the system know to search for Freetal hackers as opposed to what is, or vice versa? Like, how do you tell the system what exactly you want to search for?
Yeah, so there's like a variety of ways that you can do that. I think yeah, so I think the most simple way, if you care about like only handling very structured queries, is that you can literally like create regex to do this, right? In a lot of like quote unquote NLP out there these days, is really just like regular expressions on steroids, surprisingly, because in practice, like people really want to avoid systems that they don't fully understand. So yeah, you can do regular expressions, or you can take a question if it's more complicated, do a dependency parse on that, or constituency parse, and identify maybe the direct object.
Okay, and follow-up question from the same person. What if you wanted to search something like what does mean? So how would you differentiate the two means, one of which is a direct object and one of which is a verb?
Yeah, so surprisingly, the tools for parsing grammars that we have would probably be able to do that. So yeah, if you put that like sentence through a parse speech tagger or like a dependency parse, you would probably get tags where that would like differentiate between like the different parts of speech for that. And
So
I
it's
would
not
actually,
so it's not solely based on the meaning of the word, but it also based on like the structure of the sentence and the position.
yeah, so the way that a lot of parsers used to be implemented was that you would have sort of statistical like patterns that you would look for, right? So as you like parse through a sentence, you're computing like the probability that a verb will come after like a noun, for example, right?
Sure, sure.
And that will be very high as compared to the probability that like a verb comes after like another verb that is also like the same, that will be very low. So even though that's not how a lot of parsers are implemented today, they're usually just like black box, like neural network implementations. Those, we can think of neural networks as basically just like very complicated, like function approximators. And so then it's useful to think about like, okay, statistically, like what is the probability that like a verb will come after this other part of speech?
Sorry, I have a question.
Oh, go for it.
So when you're talking about the part one with these like regular expressions and like kind of more handcrafted methods, in practice and like in application, like they seem really brittle, and how would you like, cover up for that brittleness?
Yeah, so you're right that they do seem pretty brittle. And so, I want to go back to this idea of the data cleaning and like data sanitization step. So what people created before like general like pre-trained models became prevalent were these like databases of like words and their aliases, right? So what you would do after, like when you get like text input, is that you would clean it, you would stem it, and then you would alias it. So what that might look like for like question words is you would take like who, or you would take like who, and you would go search for all possible replacements of it, depending on its context, right? And you can think about doing this for a variety of like different ways to sort of just like express meaning, I guess. And so that would be like the most simple answer. You're right in that like there will probably always be edge cases where your system like this breaks down, but it's more about like getting broad coverage, like as broad coverage as you can, without not really about like getting like perfect coverage, if that makes sense.
Yeah, that makes sense. Thanks.
Okay, cool. Are there any other questions? Looks like no. All right, so I think we can go ahead and wrap this up. Of course, as usual, if you have any other questions, please feel free to direct them to an organizer, and we will shoot them towards Lucy. The video for this will be available on YouTube sometime within the next few hours. Share it with your friends, like, comment, subscribe, and we hope to see you all at our game night tonight for a chance to win a $25 Amazon gift card. Should be pretty cool.
Ooh, that sounds fun.
You should come. You should come. It'll be right here at I think 8 p.m.